Very similarly, we can do something with rational inequalities. And I notice this says inequalities. Let's fix that. Inequalities. There we go. All right. So what is a rational inequality? Well, it looks just like the polynomials that we had before, but it's a rational expression, meaning a polynomial divided by another. And it has an inequality in it, right? Less than, greater than, less than or equal to, greater than or equal to. So what's actually different in terms of the process? Well, if you'll look at these steps, everything is exactly the same, except for step 2. So just like before, we're going to first make sure that it's not greater than, less than, whatever a number. We have to have it 0 on the right-hand side. That's step 1. Step 2 is now, instead of just setting it equal to 0 and solving for the roots, we're now setting the numerator and denominator equal to 0 and solving. So this is basically looking for where is the roots and where is the function, the rational expression, undefined. That'll give us all of our boundary points. Then just like before, we'll create a number line. We'll break it up because of the boundary points and find test values in the intervals created. If the value is positive, then in that interval, then everything in there is positive. If it's negative, everything in there is negative. And then once we have determined all of that, we write out our solution set. So let's go ahead and take a look at an example. Also, one more thing I needed to note, the denominator, right? I said that's where the function's undefined, which means those values are not within the domain of the function. So when we are writing out our solution set, we have to recall that any values that come from the denominator are not in the solution set, which means even if our inequalities less than or greater than or equal to, at those points, we do not include them. Okay, in this problem, it's not going to matter, but we may see that here in another example. All right, so let's go through our process. It's already greater than 0, so step 1 is taken care of for us. The next step is to set the numerator equal to 0 and set the denominator equal to 0 and solve. So we have 3x equals -3, divide through by 3, and we have x equals -1. And then over here, move the 4 over and get -4, then divide by 2 and get -2. So these are our boundary values. Remember that this one is not included, even though right here it doesn't matter necessarily. Okay? Now, when I say not included, I mean in the solution set. All right? Let's take and write out our number line and break up the number line into intervals dependent upon our boundary values. So we have 0, -1, -2. These are our boundary values. So the intervals are -infinity to -2, not included, -2 to -1, not included, and -1 to infinity. So we make up our table, starting with the interval. And we have all the ones we just stated. So let's put these here. So the last one here is -1 to infinity. So we have our interval, then we need our test point, which is just a number within the interval. On the left, I'm going to use -3. Between -2 and -1, I think I'll use maybe negative, let's do maybe -3/2. And then -1 to infinity, let's just use 0. All right. Then we have our inequality. All right, plug in. So 3 times -3 plus 3 over 2x, I'm sorry, 2 times -3 plus 4. All right, so this is going to give us -9 plus 3. That's going to be -6. And this would be -6 plus 4, or -2. Negative over negative makes positive. So that number is greater than 0. So that one's good. So this is where we say include or exclude. All right, plug in -3 halves. So 3 times -3 halves plus 3 over 2 times -3 halves plus 4. All right, this is going to be -9 halves plus 6 halves. So -3 halves on top. 2 times the -3 halves would be -3. -3 plus 4 would be +1. That is -3 halves. That is not greater than 0, so this is excluded. And then finally, plug in 0. We get 3/4, which is greater than 0, so this is included. So our solution set should be -infinity to -2 and -1 to infinity. As always, I've plotted this for us. Let's take a look. So hop over to Desmos. We have 3x plus 3 over 2x plus 4. Let me just double check and make sure that's correct. 3x plus 3 and 2x plus 4. All right. So this is the inequality. We're looking for when is this thing greater than 0. So it looks like everything on this side, right, from -infinity up to our asymptote, which was x equal -2. And I'll just make that a nice dotted line. And then from -2 up to -1, that's less than 0. And then from -1 on, it appears to be greater. So -infinity to -2, -1 to infinity. Let's just go back and double check. -infinity to -2, -1 to infinity. All looks great. Let's continue on to another example. Again, this one's already solved with the 0 on one side. So step 1 of the process is taken care of. We now need to take the rational expression and set it equal to 0. And also set the denominator equal to 0. So we're solving each one separately. So we're looking for when is x equal to 0 and when is x plus 4 equal to 0. So remember, this is the denominator. Right, this one's already done. And if we just move the 4 to the other side, this is -4. Which means, again, we do not include this. And because we have an equals, right, we have to be careful. We have to take that into consideration this time. So not included in solution set. Okay. As always, make a number line. Break it up according to what we have here. There's 0. Here's -4. These are my boundaries. I'm going to pick test points. I'm going to choose -5, -1, and 1. So write out the set here. We have interval, test point, the actual equation, and whether it's included or not. So 3 intervals. The first is -infinity up to -4. Now, -4 is not included, even though it's equal for the inequality, so we use a parenthesis. Then we do parenthesis -4 to 0. We include 0. And then from 0 to infinity. Okay. Test points. We said -5, -1, and 1. Plug them in. We have -5 over -5 plus 4. That's -5 over -1, or 5. Is that less than or equal to 0? No, it is not. So we do not include this region. All right, let's plug -1 in. -1 over -1 plus 4. That's -1 over 3. Is that less than or equal to 0? Why, yes, of course it is. Therefore, that's included. And then finally, plug in 1. So 1 over 1 plus 4, that's 1/5. Is that less than or equal to 0? It is not, so we do not include this either. So it did come into play right in this situation that the -4 is not included. So if you had put the bracket for -4, you would have gotten the wrong answer. So our final answer, right, our solution set is -4 to 0. 0 is included, -4 is not. So I jumped us over to Desmos here. I've plotted the function. I've also included x equal -4, which was one of our boundaries. You'll notice that that boundary is in fact an asymptote, and this is why it cannot be included, because our rational expression can never equal that line or that point. So this inequality, right, this rational expression is greater than 0 up to that point, but then it has to skip over, and then at 0, 0, right, it's greater again. So in the problem, we were looking for when is it less than or equal to. So the solution set is just this region down here, and that's between -4 not included up to 0. All right, this is our last example. You'll notice that this is the first one we've dealt with where the right-hand side is not 0. So we do have to move the 3 over first before we do anything else. We'll do that by subtracting 3 to the other side. So this is x minus 1 over x plus 2 minus 3 greater than or equal to 0. Now, we don't like this 3 hanging out here, right? We've got to set the numerator and denominator, so we need equal to 0. So we need a common denominator. So we would multiply the 3 by x plus 2 over x plus 2. And then because they have the same denominator, we can put them together. And so we have x minus 1 minus 3x minus 6. That's going to simplify down to minus 2x minus 7 all over x plus 2. And this is greater than or equal to 0. So this is the inequality that we're now going to analyze. I need to set the numerator equal to 0 and solve. So I would add 7 to both sides and divide by -2. And I get x equals minus 7 halves. I would then set the denominator equal to 0 and solve by subtracting 2 from both sides. And I get -2. Remember, this is not included in the solution set. It possibly is a whole, or it is an asymptote, right? That's why it can't be included. Okay, break up your number line. We've got, let's put 0 over here. We've got -2 and -7 halves. right? Negative 7 halves, that's minus 3.5. So that's bigger than negative 2, at least negatively. These are our boundaries. They broke up our interval into 3 parts. Negative infinity to negative 7 halves. This one is included. Then negative 7 halves to negative 2, not included. And negative 2 to infinity. So let's go ahead and make our chart. So in the chart, we have our interval. Then we have test points. Then we have the equation. So we're doing minus 2x minus 7 over x plus 2 greater than or equal to 0. And then included or not. Okay. The intervals we've already stated. I'm just going to copy them down here. All right, so let's choose our test points. We need a point between negative infinity and negative 7 halves. Let's choose maybe negative 4. Between negative 7 halves and negative 2, I'm going to choose negative 3. And then from negative 2 to infinity, I'm going to choose 0. All right, let's plug those in. So negative 2 times negative 4 minus 7 over negative 4 plus 2. That would give me negative 8 minus 7. That's going to be, let's see, minus 15. And negative 4 plus 2, that's going to be negative 2. Negative divided by negative is going to be positive. So this is a number that is greater than 0. Right, it's not nice, but we can say it's 7.5. So that's greater than or equal to 0. So it's included. Let's plug in negative 3. All right. So negative 2 times negative 3, that's going to be positive 6. 6 minus 7 is negative 1. Negative 3 plus 2 is also negative 1. So we get 1. 1 is greater than or equal to 0. So that's included. And then we need to plug in 0. So negative 2 times 0 minus 7 over 0 plus 2. That's negative 7 halves. That is not greater than or equal to 0. So that we do not include this one. And I just noticed I made a slight mistake up here. This needs to be, oops. I want to select everything there. Okay, I'm on now. Why is this being a pain? All right, negative 2 times negative 4, that's positive 8 minus 7. So that would be a 1. And that's a negative 1/2, which is not greater than 0. So this is not included. Right? It's very rare that you're going to have two of them right next to each other that are both included. It can happen, but it's rare. So another important thing to note here is we can do this two different ways, right? We changed the initial problem into this inequality. So I went ahead and plotted this, which is, I believe, right here. Oh, sorry, right here. So this is the inequality that we just studied. X equaled negative 2 is one of our asymptotes. And the question was this inequality greater than 0? And if so, where? So according to this, it's negative 7 halves over to negative 2, negative 2 not included. And that's it, right? The rest of this curve is not going to make it above the axis. So greater is from negative 7 halves to negative 2. Negative 7 halves is included because it was equal to. Negative 2 is not included. So let's just hop back over just to double check. Right, negative 7 halves included, negative 2 not included. All right, we could also go and analyze the original inequality, x minus 1 over x plus 2. I've plotted that as well. Now notice that x equals -7/2 is right here. X equal -2 is this line here. This is an asymptote. I just plotted this so we could see quickly where we need to point. The question is, where is this greater than or equal to 3? So if I plot the line y equals 3, you'll see that starting right here at -7/2 and above, over to this asymptote, it's above 3 and nowhere else. So either of the two inequalities works. And with that, we have concluded chapter 2.